Hello everyone. Let's start a new chapter. It is chapter 2, and this chapter is basically on kinematics. Basically, kinematics in one dimension. In next chapter, you will be learning about kinematics in two dimension, and in chapter 4, you will be learning dynamics. Okay, so what kinematics means? Kinematics means how objects move. Okay, and dynamics, when you learn about when you go to chapter 4, you will be learning about dynamics means why objects move. Okay, so here in this chapter and in next chapter you will be learning how objects move. Okay, the first thing here we need to understand is reference frame or reference point. Okay, so what is reference frame or reference point? Okay, so reference frame or reference point, we need to measure, for example, distance. Okay, to measure some quantities we need some reference frame or reference point. Okay, for example, distance, if I want to measure the distance of, let's say, distance of New York City. Okay, to measure the distance of New York City we need some reference frame from where we are going to measure the distance. Okay, so for example, if I measure the distance of New York City from Scranton, so then Scranton is the reference frame, and it will be different if we measure the distance from Philadelphia, for example. Okay, so to measure distance we need a reference frame. Okay, for example, if I want to know what is the distance of your college from your home, okay, so your home is the reference frame. Okay, the simplest reference frame is the coordinate system. So you see this is the coordinate system, and many times you probably use this coordinate system. Okay, so in a two-dimensional coordinate system we have two axes, x and y. Normally the vertical is y, horizontal is x. Okay, and the left is positive x. Okay, so this is positive x, sorry, right is positive x, left is negative x, upward is positive y, downward is negative y. So this is basically our usual convention. Okay, if we do not state otherwise, I mean, if we don't say anything about the coordinate system, then this is our convention. If it is something different, then we have to mention that that what is our convention. At some point in chapter 4 you probably learn little bit different coordinate system than this. Okay, so we'll be learning that later. Okay, for the time being, so let's just focus on this simple coordinate system. Okay, so x is horizontal, y is vertical, upward is positive y, downward is negative y, rightward is positive x, leftward is negative x. Although in this chapter, because the motion kinematics in one dimension, we need either we will be using either the motion in this direction or in this direction. Okay, not both together. We will be combining these two axes in the next chapter, in chapter 3. But for this chapter our motion will be either along x-axis or along y-axis in a straight line. Okay, all right. Now before go to the next page, let me briefly talk about scalar and vector. So in this course you will be learning two types of quantities. Okay, one is scalar, another is vector. Okay, what is scalar and what is vector? So scalar can be described by magnitude only. Okay, so as if a quantity is scalar, we just need some number to represent it. Okay, for example, distance is a scalar quantity. Okay, so we just need, for example, if I want to know what is the distance of my college from my home, then let's say the distance is 5 kilometer. Okay, so we just need the 5 kilometer. Okay, on the other hand, there are some other quantities you will be learning in this course. To describe those quantities we need both magnitude, I mean both number as well as the direction. Okay, so for example, if you go left, or let's say if you go east, you have to mention that that you are going east to describe that quantity. Okay, so in the next slide we will be learning our first vector quantity. Okay, so the first vector quantity we will be learning is displacement. Okay, so the bottom line here is there are two types of quantities you will be learning in this course. Some of them are vector and some of them are scalar. To describe scalar, you just need magnitude. To describe a vector, you need both magnitude and direction. But in one dimension, so if our motion is along x-axis, let's say only along this line, then we just need either a positive sign or negative sign. Okay, so in one dimension, representing the direction is easy. So it can be represented by either a positive sign or negative sign. Let's say if something moves along the positive x direction, then the direction will be positive. If the object is moving in this direction, then the direction will be negative. Okay, but when we combine both x-axis and y-axis, I mean when we learn about the two-dimensional motion, then it will be a little bit complicated. But once you understand the concept in one dimension, it will be easier to understand in two dimension. Okay, so in one dimension it's easy. In one dimension you can represent the direction by positive and negative sign. All right, so here we are going to learn about two things in this slide. One is distance, another is displacement. Okay, so distance and displacement. Okay, all right, so to understand what is distance and what is displacement and what is the difference between these two quantities, let's consider this picture. Okay, so let's say someone starts walking from origin. So this is the origin. So origin means where x and y axis intersect. Okay, so let's say someone starts from here and the person walks 70 meter to the east. So you see the 70 meter to the east, and then the person change his mind, and let's say he walks 30 meter in the opposite direction. So he first walk these 70 meter in this direction, okay, in this direction, and then change his mind and walk 30 more meters in the opposite direction. Okay, so here he travels 70 plus 30. So the total distance he traveled is 70 plus 30, so 100 meter. Okay, so the total distance he covered or he traveled here is 100 meter. But what is the displacement? So the displacement, again, to measure displacement we need a reference frame, and displacement mathematically in one dimension we represent it by using this symbol delta x. Okay, so delta x or delta y. If the motion is along the x-axis, we use delta x. If the motion if the motion is along the y-axis, then we use delta y. Okay, so delta means, I mean delta x means, or delta y means something like this: x2 minus x1. Okay, so delta x or displacement, so let me just focus on delta x. Okay, and delta y is basically the same thing, you just replace x by y. So delta x is also called the change in position. Change in position. Okay, so you see that here the person starts from this position. So this is its initial, the person's initial position, and this is the final position. So here change in position means the final. So when we talk about changing something, so here change in position, So when we talk about changing something, the that is equal to the final quantity minus initial quantity. Whenever we have delta some quantity, remember that it is equal to final quantity minus initial quantity. So delta x, or displacement, is basically the change in position, and change in position is equal to final position minus initial position. Okay, so remember that it's not initial minus final, it's final minus initial. So x2 is final position, x1 is initial position. So this is initial position, this is final position. Okay, so in this case, so you see that here this distance is what? This distance is 40, right? So 40 meter minus 0 meter. So the displacement is here just 40 meter. Okay, so remember that displacement is the change in position, and change in position means final position minus initial position. Okay, so x2 is the final position and x1 is the initial position. Okay, so you see that the displacement and the distance are two different quantities, and here in this example the distance is 100 meter but the displacement is 40 meter. Okay, in many example you will see that the distance and displacement are the magnitude of displacement and the distance are the same. Okay, so many students confused between distance and displacement, but remember that there are two different quantities. Distance is the total distance someone covered, someone traveled, or some object traveled. Okay, on the other hand, displacement is the uh, uh, change in position, and that is final position minus initial position. Okay, so here you see that mathematically this is the equation. Okay, delta x equal to x2 minus x1. Okay, so here you see that when we talk about the displacement, it depends on the direction, right? So you see that the person goes here in this direction 70 meter, and then change the direction. So you see that displacement, when you calculate displacement, we need to know the direction, in which direction he is going. Okay, so for example, in this case the displacement is positive. So if you do this math, okay, you already see that the result is positive 40 meter. Okay, it was not negative. So positive 40 meter means the motion is in this direction, in positive x-axis. Okay, so next you will be seeing that displacement could be negative. Okay, and negative means the person is moving in the negative x direction. Okay, so let's see. Okay, all right, so because displacement depends on the direction, not only the magnitude. Okay, we need both magnitude as well as direction. So the displacement is a vector quantity. So displacement is a vector quantity. Okay, distance is a scalar quantity. Okay, so you see that the distance does not depend on the direction. Okay, so he goes in this direction and then change the direction. So even the person change his direction, we add them together, okay, to get the total distance. On the other hand, for displacement, we have to find what is the final position one and what is the person's initial position. Okay, so that's why displacement is a vector quantity and distance is a scalar quantity. All right, so here in this example you see, so here we have two examples. In one example, the left one, it shows that the distance and displacement are the same. I mean, in both cases the distance and displacement, I mean the magnitude of the displacement and the distance are the same, but in the left the distance is positive, in the right the distance is negative. I'm sorry, displacement is positive and displacement is negative. Okay, so how? So if you start from this position 10 meter and if you stop here at 30 meter, so your displacement here is delta x equal to x2 minus x1. So x2 here is 30 meter, right? So this is 30, and x1 is 10 meter. So this is just 20 meter, and it is positive. So here the displacement is 20 meter, and from here to here the distance is also 20 meter. Okay, so you see in this case the magnitude of the displacement and the distance are the same. Okay, in some example you will see that the distance and the distance and the magnitude of the displacement are the same, but even though in some example they are the same, but uh, but these are two different quantities. Okay, so in the left we see that the displacement is positive. Now here in the right you see the person starts from 30, so this is x1, this is the initial position, and stops at 10. Okay, so if I calculate x2 minus x1, I get 10 minus 30. So final always fast. Okay, final minus initial. So what you get 20 meter, minus 20 meter. Okay, so minus sign tells us that the person is moving in the negative x direction. So in the first case, the person is moving in the positive x direction. In this case, the person is moving in the negative x direction. That's why we have a negative sign here in the right one. Okay, but in both cases, the distance is 20 meter. Okay, all right, remember that distance and displacement, distance and the magnitude of the displacement sometime can be the same, but they are two different quantities. Okay, do not confuse one with other. All right, so both distance and displacement are measured in meters. The standard international unit for distance and displacement both are meters. Okay, and as you already know that we use m for meter, small m for meter. All right, the next thing is average velocity. Okay, so here you are going to learn speed, average velocity, and then instantaneous velocity. Okay, so what is average velocity? So the mathematical definition of average velocity is this one. So the average velocity is distance travel divided by the travel time. Okay, so uh, you see that here in the average speed we use distance. Okay, so distance travel divided by the travel time. So because average speed is associated with the distance, and distance is a scalar quantity, average speed is also a scalar quantity. Okay, on the other hand, average velocity is this. Average velocity is displacement over travel time. Okay, and you already learned that displacement is a vector quantity. So because average velocity is associated with displacement and displacement is a vector quantity, so average velocity or velocity is also a vector quantity. So speed, average speed, or any speeds are scalar quantities because we need distance to measure speed. Okay, to measure velocity we need displacement. Okay, so because we need displacement for velocity, it is a vector quantity. Okay, remember that they are again two different quantities. Average speed and average velocities are two different quantities. Okay, mathematically average velocity is written by using this equation. Okay, v bar. So bar means average. So in mathematics, by using a bar, we basically show that that the quantity is average quantity. Okay, so when we have a bar on top of some quantity, it means we are measuring or we are calculating the average quantity. Okay, so v bar means the average velocity, and average velocity you already know that the displacement delta x, the change in position over the travel time. Okay, so delta x over delta t is the average velocity. Okay, all right. Now, although they are two different quantities, okay, the standard international unit for both are meter per second. Okay, so that's because we have distance on the numerator here and we have displacement on the numerator here. Okay, and both can be represented by using meter, and the time is the standard unit for time is second. So the standard unit for average speed and average velocity are meter per second. Okay, all right. Now, what is the direction of the velocity? So because the velocity is associated with displacement over travel time, the direction of the velocity will be the direction of the displacement. If the displacement is positive, the velocity's direction will be positive. Okay, if the displacement is negative, okay, the direction of velocity or average velocity will also be negative. Okay, so the direction of the average velocity is the same as the direction of the displacement. All right, now let's try to solve this problem. Okay, so let's say a girl cycles a circular track of diameter 70 meter and stops at the starting point. Okay, so she starts from here and she stops here. Okay, we have to find what is the distance travel. So the distance travel is basically, so because she starts from here. Okay, so she travels this distance. Okay, so what is this distance? This is basically the circumference of this circle. Okay, and you probably already learned in math class that circumference can be circumference of a circle is just 2 pi r. So here r is the radius. Okay, so what is the radius? So this is diameter. Okay, so diameter, if the diameter is 70 meter, radius will be half of this. So because it is 70 meter, the radius is 35 meter. Okay, so the total distance here will be 2 pi r, and 2 pi r means 2 pi times 35 meter. Okay, if you multiply this using your calculator, you should get something like this. So the distance she travels is 220 meter. Okay, very good. Now this is tricky. What is her displacement? Okay, so many students make mistakes. They put this 220 meter, but that is incorrect. Okay, so the displacement, remember the displacement delta x is initial final position minus initial position, and here initial and final position both are the same. Okay, so both are the same, so the displacement here is equal to 0. Okay, so this is tricky. So remember that when the starting and final position both are the same, the displacement is equal to 0. Okay, now what is the average speed here and what is the average velocity? Okay, so average speed, so this is 0 meter, so average speed will be speed, avg speed is the total distance. So she traveled this much distance in 35 seconds. Okay, so this is the average speed, so it is about 6.28 meter per second. Okay, and average velocity is equal to displacement delta x over delta t. Okay, delta x equal to 0 and delta t is 35 seconds. So average velocity is 0 as well. Okay, so because the displacement is 0, the average velocity is 0, but the average speed is not 0. Okay, so try to understand these. So average speed I mean, we can have average speed, but average velocity could be zero, even we have average some value for the average speed. Okay, so this is one of the example. And in class what, we will be doing some more example about that. And you will be doing some homework, similar homework problem. Okay. So we see that average speed and average velocity are not the same. Okay, but sometime similar to the distance and displacement, sometime average velocity, I mean the magnitude of the average velocity and average speed could be the same thing. Okay, same number. Okay, we will also see some example where you will see that the magnitude of the average velocity and the average speed are the same number. Okay, but the thing is they are two different quantities. Even sometimes they are the same, they are two different quantities. All right, so the instantaneous velocity. So the next thing is instantaneous velocity. Okay, so here I show a car speedometer. Okay, so the car speedometer, so when you drive, the car speedometer basically does not show the average velocity. Okay, it basically show the velocity at any particular instant of time. Okay, so you see that always it changes. Okay, the speed on the speedometer, okay, it always changes. Okay, what it means, it basically shows us the instantaneous velocity. Okay, so the velocity at some particular instant of time. Okay, now how to mathematically define instantaneous velocity? Mathematically it is something like this. Okay, so v, the average velocity, is this, right? Now when this time is very small, infinitesimally small, okay, then average velocity is basically the instantaneous velocity. When time is very small, it means we are basically focused on some particular instant of time. Okay, so that's why when time is small, average velocity is basically the instantaneous velocity. And mathematically we write this as this: v, the instantaneous velocity. For instantaneous velocity we do not use bar on top of it. Okay, and limit delta t tends to 0, that means delta t is very small. Okay, so when delta t is very small, the velocity we get is the instantaneous velocity. Okay, all right. So here we show two graphs. Okay, so this is easy to understand. You see that it is constant. Okay, so if we have a graph something like this, it tells us that the instantaneous velocity and average velocity are the same. Okay, so at any instant of time, for example, you are interested on at this instant, um, okay, so here it is 40 kilometer per hour. At this instant it is also 40 kilometer per hour, and at the same time the average velocity is also 40 kilometer per hour. Okay, but for the next graph you see that it is not that straight. It goes up and then straight and then goes down and then straight and then goes down. Okay, so in this case the instantaneous speed are different at different instant. For example, if you, so here the instantaneous velocity is 30, here it is 50, here is again 30, here it is 20, and so on. So the instantaneous velocity changes with time, but the average velocity will be the average of all those things, all those velocities. Okay, so here you see the average velocity is this one. Okay, all right, so you see that sometime average velocity and instantaneous velocity are the same and sometimes they are not. Okay, all right. The next thing we are going to learn is called acceleration. Okay, so to represent acceleration, we use a, small a, for acceleration. Okay, small a for acceleration, remember that. So you know that we accelerate our car, right? We accelerate our car. So when we speed up, that means we are accelerating our car. Okay, when we slowing down our car, that means we are deaccelerating. Okay, so one is accelerating. Accelerating means we are speeding up. Deaccelerating means we are slowing down. Okay, so what we do when we speeding up, so we basically change the speed, change the velocity. Okay, so speeding up is acceleration and slowing down is deacceleration. So when we speed up, okay, we basically or slow down. In both cases, we basically change our velocity. Okay, so the definition of acceleration or average acceleration is change in velocity divided by the time. Okay, so remember that acceleration, the physical meaning of acceleration is speeding up or speeding down, but mathematically it is the rate of change of the velocity, okay, at which the velocity is changing with time. Okay, delta v, delta t. And again, you know that delta v is something like this: final velocity minus initial velocity. Time is also final time minus initial time, right? Because this is the change in velocity, the numerator is change in velocity and denominator is change in time. Okay, delta v means change in velocity. Okay, so final quantity minus initial quantity. So acceleration can be written as something like this. Okay, so the definition of acceleration is the rate of change of velocity, or the rate at which velocity is changing with time. Okay, and now here we have velocity. Okay, so in the definition, in the mathematical definition of the acceleration, we have velocity, and velocity has velocity is a vector quantity. So acceleration is also a vector quantity. Okay, so you see that acceleration can be derived from velocity, okay, from this simple equation. Okay, as velocity is a vector, acceleration is also a vector quantity. Okay, now what is the unit, standard international unit for acceleration? The unit or standard international unit for acceleration can be derived from this equation. Okay, so you know that the unit for velocity is meter per second and unit for time is second. Okay, so meter per second and another second in the denominator, so it is all together meter per second square. So we have 2 seconds here. Okay, meter per second square. So the standard international unit for acceleration is meter per second square. Okay, so in velocity we see that the direction of the velocity is basically same as the direction of the displacement. Okay, here it is little bit different. Okay, so let's see how it is different than the earlier concept we learned. Different than velocity. Okay, all right, so to understand this, let's consider these two examples, the left and the right. Okay, so in the left, the car is at rest. Rest means the car's velocity at initial time t equal to 0 is 0. Okay, so the initial velocity for this car is 0, and then we start this car, and at time t equal to 1 second, okay, the velocity is now something different. Okay, 15 km/h. Okay, so here you see that first the car is at rest. After 1 second, the car's velocity is now 15 km/h. Okay, so in 1 second its velocity is increased by 15 km/h. So because it increased, that means we are speeding up. So when speeding up, that means we have, we accelerate this car. Okay, so what is the acceleration then? The acceleration will be v2 minus v1 and delta t, or t2, or t2, t2 minus t1. Okay, so delta t here is basically 1 second, and v2 is 15 kilometer per hour, and v1 is 0. So it is basically 15 kilometer per hour per second. Okay, so here we have two different unit for time. Okay, one is hour and second. We can convert those in one unit, but let's focus, let's now focus only on the concept. Okay, we'll be doing conversion when we do the classwork problem. Okay, so here what happened, the car was at rest, and then at 1 second the car's velocity increased to 15 kilometer per hour. So the what it means, because here you see that the car's velocity increases, that means we are speeding up the velocity. We are speeding up the car, so that means we are accelerating the car. And what is the acceleration? Acceleration is final velocity minus initial velocity. Here final velocity is 15, initial velocity is 0, and then delta t is again final time minus initial time, and that is equal to 1 second. So you see that we get some value for the acceleration. Okay, now here you see that the value for the acceleration is positive. Okay, so when we see the positive value, okay, when we have when the car's velocity increases, okay, then the direction of the velocity and the direction of the acceleration will be the same. Okay, so you see that here the direction of the velocity, so the velocity, the car is moving in this direction. Okay, so that means it is moving in the positive x direction. Positive, the sign for the velocity is positive. Okay, and after calculation we get a positive number for the acceleration, and this positive number tells us the direction of acceleration and the direction of velocity are the same in this problem. Okay, so when we speed up, okay, speeding up means the direction of the velocity and the direction of the acceleration are the same. Okay, now let's consider this problem now. So here you see the initially the car was running at 15 meter per second. Okay, so initially the car is moving at 15 meter per second, and then we probably hit the brake, and after 5 seconds the velocity becomes now 5 meter per second. You see that we are slowing down. Okay, slowing down 15 to 5. Now if I calculate the acceleration, v2 minus v1, t2 minus t1, or delta t. Okay, so v2 is 5 meter per second, v1 is 15 meter per second, right? T2 is 5, t1 is 0. So what we get here, we get minus 10 meter per second divided by 5 second. So what we get, minus 2 meter per second square. So now this minus sign tells us the direction of acceleration is towards the negative x direction. So in this direction. Okay, so this is the direction of acceleration, this because of this minus sign. Okay, but you see that the car is moving in this direction. The green arrows are car's velocity direction. So car is moving toward the positive x direction. Okay, but what we get for the acceleration is the direction of acceleration is toward the negative x direction. Okay, so here you see that the yellow line tells us about the direction of the acceleration, and the green line is about the direction of the velocity. So when we slowing down, okay, the direction of the acceleration, also we call it the deceleration. Okay, so the direction of the acceleration is opposite of the velocity. Okay, so speeding up, when we speed up, the direction of velocity and acceleration are the same. When we slowing down, the direction of the velocity and the direction of the acceleration are opposite of each other. Okay, so one more example here. You see that initially in this, so let's look at this problem. Okay, so you see that the car is now moving in the negative x direction. Okay, so car's initial velocity is -15. Okay, so negative because it is moving in the negative x direction. It's slowing down, so after some time its velocity is now -5 meters per second. Okay, and let's say to go from here to here, let's say we need 5 seconds. Okay, so similarly we can calculate the acceleration is v2 minus v1 divided by t2 minus t1. So v2 here is -5, v1 is -15. Okay, so we have here two negative sign. Okay, one is this minus and another is the sign of velocity, and t2 is 5 second minus 0 second. Okay, so what you see here is minus and minus plus, so -5 plus 15 is +10 divided by 5. So what we get is 2 meters per second square. So what we get here is positive sign for the acceleration. Okay, and positive sign tells us that the direction of acceleration is toward the positive x-axis. Okay, and here you see that it is slowing down, -15. Initially the velocity was -15, the finally the velocity is -5. So here the slowing I mean we are slowing down our car. Okay, -15 to -5. Okay, so as you already learned, when we slow down our car, the direction of acceleration will be opposite of the velocity, and that what we see. Okay, so we get a positive value, and positive value tells us that the direction of acceleration will be towards the positive x-axis. Okay, and it makes sense. All right. All right, the next thing is the instantaneous acceleration. So similar to the instantaneous velocity, we can have also instantaneous acceleration, and instantaneous acceleration is basically the acceleration at a particular instant of time. And similar to the instantaneous velocity, we can define mathematically the instantaneous acceleration as this. Okay, so when delta t is very small, then the average acceleration is basically the instantaneous acceleration. And for instantaneous acceleration, we do not use the bar on top of a. Okay, all right. Now the next thing is 4 important equation. So to solve the problem, okay, we need some equation. I mean, all the thing you learned so far can be summarized into 4 equations. Okay, so if the object moves in a straight line, okay, so if the object moves in a straight line, okay, and if the object's acceleration is constant, okay, if a is constant, okay, average acceleration is constant. So when average acceleration is constant, then you can write something like this. I mean, the instantaneous acceleration and average acceleration should be the same. So when object moves in a straight line, and if the object's acceleration is constant, then all the thing you learned so far can be summarized into 4 equations. Okay, so we call these 4 equations as kinematic equations, or all the whole thing we call it a straight line motion at constant acceleration, equation of the straight line motion at constant acceleration. Okay, or altogether it's just the kinematic equations. Okay, so here I derive it. If you want to know, you can just go through the study guide. Okay, here I'm not going to explain how I derive it. I'm going to explain just the final form. Okay, so here we have this final form. Okay, so these are the four equations. Okay, so these are the four equations, and these four equations we call it kinematic equations. And in this course, you will be you will be seeing that these four equations we are using so many times. Okay, so it's better to understand what I mean. It's okay if you don't want to um, um, know how I derive it, but it is important to know what what quantity means what. Okay, so in this four equation, x is what, x0 is what, v bar is what. So you should understand this. Okay, if you understand this, it will be easier to solve any problem. I mean, any related problem. Okay, it's okay if you don't want to understand how I derive it, but it is important to understand which symbol means what. Okay, so here, let's say our object is moving in this direction, that means in x direction. Okay, so let's say x is the final position of the object, x0 is the initial position of the object. Okay, so x is the final position, x0 is the initial position, t is just time, running time. Okay, and for final position, the final velocity is v, initial position, the initial velocity is v0. Okay, and if a is the acceleration, constant acceleration, then we can write that x equal to the final position equal to x0 plus v bar t. So here v bar is the average velocity. Okay, and average velocity is basically in this case is v plus v0 over 2. Okay, and then the next equation tells us that v equal to v0 plus at. V means the final velocity, v0 means the initial velocity, a is the acceleration, and t is the running time, and so on. Okay, so here again, x is the final position, x0 is the initial position, v0 is the initial velocity, t is the running time, and a is the acceleration, and so on. Okay, so important thing here to understand is these four equations we can use when our object is moving in a straight line. So because it is x, that means the object is moving along the x-axis. Okay, with a constant acceleration. Okay, if the acceleration is not constant, then we cannot use this equation. Okay, but I mean, most of the problem we will be solving in this chapter are with constant acceleration, so you don't need to worry about non-constant acceleration. Okay, now, so here this four equation is for when the object is moving along the x direction. Okay, so how about if the object moves in the y direction? So if the object moves in the y direction, then you have to replace x by y. So that's it. So you have to understand that now the object is moving in the y direction, in the vertical direction. So you have to change the notation. Okay, so here here you see that these four equation I wrote separately. Okay, one set for x and one set for y is basically the same thing, but because now we have both x and y, so instead of just writing v or v0, I wrote vx, vx0, and vy and vy0, also ax and ay. Okay, to differentiate the motion along the x-axis, I mean equation along the x-axis and equations along the y-axis. Okay, so it's basically the same thing. Okay, one set is for motion along the x-axis and this set is along the motion along the y-axis. Okay, all right. The next topic is the falling object. So as you know, when you drop something, okay, it goes downward. Okay, so why it goes downward? Because earth pulls everything downward. Okay, now let's say we drop two things together. Okay, so let's say we drop one ball, tennis ball, and a piece of paper. Okay, so from our common sense, okay, we know that the tennis ball will hit the ground first. Okay, and then the paper. Okay, so why? Because that we are going to understand. Okay, yeah, so why the paper hits the ground later? Because there is something that raises the paper to fall faster. Okay, and that something is the air resistance here. Okay, so if we do this same experiment somewhere where there is no air, for example, if you do the same experiment on the surface of moon, okay, as you know that on the surface of moon there is no air. Okay, so if we could do this experiment, in fact scientists already performed this experiment on the surface of moon, and they found that the both, I mean they use on the surface of moon they use a hammer and a feather. Okay, so so if you do the experiment here on the surface of earth, hammer will hit the ground quickly. Okay, and then the feather. Okay, but if we can do this experiment where there is no air, like on the surface of moon, you will see that both will hit the ground at the same time. Okay, and that's because the moon pulls everything at the same rate. Okay, so if there is no resistance due to the air, okay, then earth basically pull everything toward it at the same rate. Okay, the same rate of acceleration. Okay, so the rate at which earth pulls everything downward, we call it the acceleration due to gravity. Okay, the rate at which earth pulls everything downward, we call it acceleration due to gravity. Okay, and we use the symbol G for gravity. Okay, gravitational acceleration, the acceleration due to gravity or the gravitational acceleration, and the value of gravitational acceleration is 9.80. And this is because, I mean, because it is the acceleration, the standard international unit is meter per second square. Okay, this is a standard value. Okay, so we'll be using throughout in this course. So if it is due to the earth's gravity, the gravitational acceleration is 9.80 meter per second square. Okay, so what it means earth pulls everything downward at this rate, at this acceleration. Okay, and because the direction of this acceleration is always downward, right? Because object falls downward, the direction of G is negative. Okay, remember that the direction of the gravitational acceleration is negative. Okay, now to mathematically explain the gravitation, I mean the freely falling object. Okay, I mean when something falls downward, and if we ignore the air resistance, okay, then we can use the kinematic equation to explain the motion of freely falling object. Okay, so the one thing here we have to add it is we have to ignore the air resistance. Okay, so if you consider the air resistance, then it will be a little bit different. Okay, but if you ignore it, then we can just use some of the kinematic equation to explain the motion of the freely falling object. Okay, so what are those equations? So let me write down here. Okay, so we basically need the second, third, and fourth equation. The second equation was V equal to V0 plus AT. Third equation was x equal to x0 plus V0t plus half AT square. And fourth equation is V square equal to V0 square plus 2a x minus x0. Okay, now when we deal with the falling object, and if we ignore the air resistance, then a is basically gravitational acceleration. Okay, and the sign of the gravitational acceleration is downward. Downward means negative. Okay, so what we do here, we basically change the symbol a and this sign. Okay, so it will be now minus g minus g minus g. Okay, so you see that we started from the kinematic equations number 2, 3, and 4, and we replace a by g, and then also replace the sign in front of g by change the positive sign to the negative sign. Okay, because the gravity is always downward, and downward means negative in our notation, in our convention. And also because it is the free fall happen in the vertical direction, so we should also change x to y. Okay, so let's change this. Okay, so the equation will be this: y equal to y0, okay, and then y minus y0. Okay, so these are the three equations we need to explain the freely falling object. Okay, now so when we drop something downward, okay, it's of course the freely falling object. Okay, but when we throw something up, it's also under the free falling, under free fall. Okay, why? So when we throw something up, okay, just after we throw something up, okay, if we ignore the air resistance, okay, then the object is just under the influence of gravity. Okay, so when we throw something up, it goes up, 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 and then it comes down because earth pulls that object downward. Okay, so even we throw the object up, okay, it comes down because gravity, because the earth pull that object downward. Okay, so that is also under free fall. So we can explain that with this equation, with these three equation. Okay, so if you throw something some object upward, okay, if you ignore the air resistance, then again to understand the motion of that object, you can use these three equations. All right, the last thing here we want to know is the graphical representation of the motion. Okay, all right, so the next slide. Okay, so here I talk about this. Okay, the three equations. Okay, now you already know how you can get these three equations. Okay, now the last thing is the graphical analysis of linear motion. Okay, so linear motion means the object moving in a straight line, either along the x-axis or vertically. Okay, so non-linear motion is a little bit complicated, and we are not going to discuss non-linear motion in this course. So our motion is linear, and that is along the straight line. Okay, either along the x-axis or along a y-axis. And for simplicity, we just consider very simple cases, okay, where the acceleration is constant. Okay, all right. So if we plot a graph, position versus time, okay, so position along the x-axis and time along the y-axis, we get something like this. I mean, for a simple situation, for example, um, let's say we start from 0 at 0 second, our position is 0. Let's say at 1 second we walk, let's say 10 meter, okay, so 1 second 10 meter, 2 second 20 meter, and so on. Okay, so this is basically the position versus time graph. So if you walk starting from some point, and if you use stopwatch, you can do this. You can get the numbers and you can plot in a graph paper. And let's say the graph of your position versus time looks like this. Okay, although this is a position versus time graph, it can give you some important information about your velocity. Okay, so when you have a position versus time graph, if you determine the slope, okay, if you can determine the slope, okay, slope is basically rise versus run. Okay, so rise is basically here delta x over delta t, and do you see that delta x over delta t is velocity, right? I mean average velocity. So if you can determine the slope of a position versus time graph, you basically get the average velocity. Okay, so when we have a straight line of a position versus time graph, find the slope, and that slope will tell you about the average velocity of your motion. Okay, now now what is delta x delta t? Okay, so from the graph, how you determine the slope. So delta x is basically x2 minus x1, and delta t is t2 minus t1. So you see that I mean, to determine the slope, you basically need 2 points. So you choose 2 points. Let's say you choose this point and this point. Okay, so this is final and this is initial. Okay, so this is x2. Okay, so the x2 is this one, and this is x1. Okay, so x2 probably 45 and x1 probably 32, and this is t1 and this is t2. Okay, okay, so so plug these values here in this equation and you get the slope. Okay, and slope basically tells you about the velocity, average velocity of this graph. Okay, now sometime we may have velocity versus time graph. Okay, so this is a position versus time. So position versus time graph basically gives you the velocity. Now if we have a graph that is velocity versus time, okay, so if we have a velocity versus time graph, the slope of this velocity versus time graph is delta v delta t, right? So v is the rise and t is the run. So what it is basically the average acceleration. So if we have a position versus time graph, we get average velocity. If you have a velocity versus time graph, we get average acceleration. Okay, so remember that. And the last thing here for today is this graph. So here you see that we have a velocity versus time graph. Okay, and the velocity versus time, the slope of the velocity versus time graph is the acceleration. So we can determine the acceleration here, okay, and also here. Okay, but the important thing here, I mean interesting thing here, because here there is no rise. Okay, I mean if we choose this point as x1 and this point x2, you see that x2 minus x1 is the same value, is 12. Okay, so 12 minus 12 is 0. So when you have a straight line that is parallel to the x-axis, the slope of this graph is equal to 0. So what it means? It means the acceleration at this region is equal to 0. So there is some acceleration here, but there is no acceleration here. Okay, so here we are talking about the acceleration because we have this is a velocity versus time graph. Okay, so because this is a velocity versus time graph, here we have acceleration, here there is no rise, so the acceleration is 0. Okay, if it is a position versus time graph, then we basically talk about velocity, not the acceleration. The slope that time it's the velocity, not the acceleration. Okay, so remember that, and that's it for today. Okay, we'll be doing a problem, the classwork problem, in the next class.